Okay, so our next task is to prove the correctness of Bellman-Ford, and it turns out that it's useful to modify slightly the algorithm. So the classical setting, the loop goes to n minus 1, but in fact it's easier to think about the version where we go up to n. This is only for analysis purposes, although, it doesn't affect the asymptotic running time because the running time remain with our notation the same. Okay. So the first observation is that dvk, right, the length of the walk that uses k edges to v starting at s of length at most case k, this value is computed correctly. Namely, it is indeed contained the length of the shortest walk using at most k edges from s to v, and the proof of this is an immediate proof by induction, right? It's very easily, maybe you don't know, so let me say that. So you start with the source, and for value 0, only the source has a path of length 0, so the base of the induction is obvious. Now you assume that everything was computed correctly to k minus 1, and you look on the vertex v, you look on the shortest path to it of length k, and you observe that at some point there is a previous vertex u on this path, and the dynamic Bellman-Ford would take du k minus 1 plus duv, luv, and try to update this value to d, right, to dvk, when computing dvk. And in particular, it would consider this value, which means that the value stored in dvk is going to be smaller than the length of the shortest walk that end up at v. On the other hand, whatever value is stored there is the length of a walk of length at most k. Again, you need to convince yourself by induction that this is true, and as such, we are done, right? Because it stores a value that is shorter, smaller than the desired quantity, and on the other hand, it cannot be smaller than the desired quantity, so it must be the desired quantity. So that's the inductive proof. So we omit it. It's easy. Maybe I should not have done it, but that's okay. The more interesting claim is the following. And the claim is that the distances stabilizes. What do I mean by that? The dvn is equal to dvn minus 1 for all the vertices, assuming there is no negative cycle in the graph. And as such, in particular, since it stabilizes, dvn minus 1 is in fact the length of the shortest path between s and v in the graph. Okay, so why is this true? Well, consider the shortest walk from s to v, independent of the number of edges, right? So there are two possibilities. Either it's a simple path, and then it have at most n minus 1 edges, so that's great. The other possibility is that it's not a path, but it is instead has a cycle in it. But if it has a cycle, the only possible reason why to take a cycle is because the cycle is negative, right? But we are assuming there is no negative cycle in the graph, so it's not possible. So the shortest walk in this case is also a path, right? So all the shortest walks are shortest path. They have length n minus 1. We just argued that Bellman-Ford compute correctly the length of the walk dv n minus 1, which implies that indeed dv n minus 1 contains the length of the shortest walk from s to v. Now, this in particular implies that dvn and dvn minus 1 are equal because you're not benefiting for having a walk with n edges, right? It's still going to be, the shortest one is still going to be of length n minus 1, so those two quantities must be equal, and that's complete the proof. Okay. Okay, so we proved, what did we prove? We proved that if there is no negative cycle in the graph, then Bellman-Ford compute the shortest path from S to all the vertices in the graph correctly. Now we want to understand how to handle negative